A very good afternoon to one and all. I'm Ankita Chauhan from NASSCOM. So let's begin the second episode of our data science series on the topic Building Machine Learning Model from Scratch, Theory and Tutorial. It will be presented by Dr. Deshmukh, who is a Senior Director in the Analytics Center of Excellence at Envestnet, Yodlee. You can write your questions anytime during the session, which we would be taking care first few questions in the middle of the session and the remaining ones at the end of the webinar, depending upon the time as well as the number of questions we have in our kitty. Also, please do not forget to provide your feedback to help us improve our future sessions. So yes, let's begin. Over to you, Om.
Thank you, NASSCOM, and thank you, Ankita. Hello, everybody, and thank you for sparing time to join this session. Like Ankita said, please do send your questions. We'll take a short break right in the middle of the presentation to try and answer a few questions, and then again towards the end we'll take more questions. Okay, so what I wanted to do was, before we get into the details of what does it mean to build a machine learning solution or a machine learning end-to-end product, I wanted to address one issue which which we as machine learning professionals see all the time in our field, which is 100% accuracy. At what point can we get 100% accuracy? And so when I get asked this question, I typically ask a counter question, which is, how do you define 100%? And it sounds very simple, but I'll give you one example, hopefully, which will illustrate that the definition of 100% is quite elusive. So what you see on the screen is a Google search screen, and I'm searching for Jaguar. And I'm showing you an image that comes in response, which is the Jaguar car. And what I'm hoping is all of you will agree that this is indeed the right result. But is this the only right result? Probably not, because there could be this animal that you were expecting when you search for Jaguar. So that's also equally correct. But now there is a slightly non-obvious error, quote unquote error, which may have happened, which is the following: that maybe you were really looking for this bathroom fitment, you searched with a slight spelling mistake, and you really were hoping that the system will be quote unquote intelligent and will help you correct the question that you are asking. And so this is the gray area where a lot of the times machine learning solutions have to play. And so a part of building the machine learning solution goes into identifying what is the gray area that you are working in, which also ties in with the UI UX part of it, which I'll touch upon towards the end of the presentation. So while these are cases where the answer is definitely correct or maybe correct, there are areas where the answer is definitely wrong. So in response to this query of Jaguar, if I show you a image of a flower like this, that's definitely wrong. And so if you make mistakes like this, then that is what I call as bringing bad name to machine learning. Yeah. Okay. So I wanted to just set the context for what a machine learning end solution should do and shouldn't do. Moving on, in a typical environment, what is the way in which decisions are made? Before the advent of big data, the decisions were typically driven by hippos, right? Highest paid person's opinion. And it was rightfully so, because there was very less data to work with, even fewer tools to analyze the data and come up with actionable insights. And so you would rely on the person's intuition, that person's advisors and their intuitions, and also the domain expertise that these group of people have gathered over the years of their experience, and that was also what was highly paid for, right? And then that based on those insights you would drive a particular action. Now what has happened is, as the data has come through, this decision making process has changed. And so the executives or the people who are part of the decision making community have also had to change their approach towards the problem. Instead of just going in with, I know all, I have a gut feeling, let me solve it how I used to solve it 10 years ago, the approach has to now change towards the decision makers or decision influencers to now say that we will formulate our hypothesis based on what we know, based on our domain knowledge. Let us now evaluate these hypotheses, and here's a plural that we have formulated. But the minute you say you want to evaluate these hypotheses, you have to figure out which data sets are of relevance. Do you have those data sets? Are there tools to evaluate the hypothesis? Once you have the findings, are there ways in which you can rank them, and so on? This is all where machine learning comes in. And then once you have the insights, you also have to call out the caveats. For example, if the data is biased towards a uh, particular decision, you have to call that out. If the data is biased in the sense that it doesn't represent the entire universe that you would like to represent, that also has to be factored in before a decision is made. Finally, the expert now has to interpret the data or the findings. This is often ignored or often not given as much value as it should be, that the interpretation really has to lie with the expert, who then has to figure out what is the actionable insight that he or she has to drive out of this data making exercise. So that's sort of the gamut of things that go into making a data driven decision. What we've been doing over several years now is trying to formulate, just like we have software development steps, we are trying to formulate what are the n number of steps that you would have to go through to solve or to create a product which is machine learning or AI or data science driven. So what you see on this slide are 9 steps that we've formulated, which will help you go from the beginning all the way till end, where you have a deployment ready ML driven solution. So what are these steps? I'll very quickly walk you through those, and then I'll cover some of them in detail. In the interest of time, I won't be able to go through all 9 of them. So the first problem or the first step in this journey is knowing exactly which problem to solve. See, half the energy goes in just figuring out what is the problem of relevance. When you're doing toy problems, and I call them toy because those are not really real life problems. What happens in those cases is the problem is given to you. For example, you are given a bunch of images and you are asked to uh, distinguish or discriminate between a cat's image and a dog's image. So the problem is already given to you. This very rarely happens in the real world. So that's the first. The second step is, now that you've formulated the problem, you have to go hunt for the data. Where does the data lie within your within the corporate setup, or how do you, if the data doesn't exist, how do you create that data? What are the limitations that that the data poses? The third step is, once you figured out the data, you need to scrub the data. What that means is normalizing it so that the relevant columns are present, relevant holes are imputed. There's a process called data imputation and so on. The fourth step, which is where I'll spend a lot of the time today, is you have to now formulate the problem in the context of the data in such a way that one of the existing ML frameworks can be utilized. And this is by far the most difficult thing to do. But the funny thing is, it is obvious in hindsight. What I mean is, once you've once you formulated the AI/ML framework that you want to use for solving the problem, everybody who will look at it will say, oh yeah, this was obvious. We knew exactly this is the way to solve it. But when you start the journey, it's not obvious at all. The fifth step is swimming through the data, and this is a terminology that we've termed in Yodlee. What this essentially means is just looking at the data from different angles, formulating some hypothesis, going back, creating more slices of data, passing it through step 4 of the AI/ML framework, and maybe changing the framework itself. And that's, like you see here, is an iterative process. The sixth step is representing this data so that the machine can consume it. 7 is training the ML framework so that the outcome is generalizable, and I'll give you some examples of it later on. And then also be able to deploy it so that the solution is not prohibitively expensive. And expensive need not just be from a cost perspective, it can also be time. Sometimes when you expect real-time outputs, taking 30 seconds, even though accuracy is 99.9, is expensive and not feasible. The next component is that of UI UX. And again, I'll give you some examples of how this last mile connectivity of UI UX is crucial. Lack of it can expose the inefficiencies of the ML system that you've built. And then the ninth and the final step is, because the data is dynamic and because the world itself is dynamic, your systems, if left static, will see a drop in accuracy. And so you have to regularly check for the dynamic nature of the data, how it is impacting the accuracy of your system, and provide those feedback, and essentially then upgrade the solution, which means go back to the drawing table, start from problem 1. Okay, so moving on, let's start with the first problem. First step rather is knowing exactly what the problem is. This is where what we do at Yodlee is what we call as the discovery phase, which means we work closely with the product teams, with the domain experts. Sometimes also have dreaming sessions with our clients and partners to understand what it means to be solving a particular problem. See, oftentimes, and most of you all here in this session will also face this, is the problem that is given to us as the data scientists or as the machine learning experts is a business problem, which says increase my throughput, or help me reduce my churn, or help me figure out what is the next product that a particular customer is going to buy, and so on. It's a very abstract, very business driven problem. What then has to happen is you have to formulate this into a functional problem, which is something that is tangible, that you can measure the outcome in an unequivocal way, and then translate from that functional problem to what we call as a data-driven problem, which means this is the data that I'm going to use. If I get this data, this is how I'm going to define success. And if I don't meet that success, this is how I'm going to try and improve. So going from business problem to data problem is what I call as the first step of defining exactly what the problem is to be solved. The next is the data itself, which then says, as you've now formulated your problem, in the ideal world, what is the data set that you would expect? Most often you will not get the ideal data, either because it lies in a variety of different silos. It's not possible to get the data across all of these silos, or some of the data just doesn't exist. And so then you have to settle for what we call as the practical elements of the data, which will then lead to A, holes in data, or B, biases in your data. What do I mean by biases? Holes is pretty obvious, I guess. What do I mean by biases? Let's say let's say in the healthcare domain, you are looking at a hospital's data of what causes some sort of a heart condition. And now, obviously, the hospital is going to give you 90% of the data where the heart condition doesn't exist. And rightfully so. Hopefully we live in a relatively healthy world where 80 to 90% of the population, can catch these ailments or conditions early on before they become critical. So the bias is very strongly present in your data towards not pointing towards a deteriorated or an extreme condition. So you have to be very cognizant of what is the bias that your data is bringing. I'm going to very quickly gloss over this. The idea is how can you impute data, how can you scrub it so that the generalizability remains. And the example I was giving is you don't have to look at all the 6 billion human faces just to know what a human face looks like. Now the fourth step is as I mentioned earlier, is the most difficult step, but what compounds the problem is it's obvious in the hindsight. And so while we may feel the pressure to come up with a solution quickly just because it may look obvious in the hindsight, what I would encourage everybody here is to spend the most amount of time just really figuring out what is the solution that is optimal for this problem. There are a couple of things that everybody should be cognizant of. The solution has to be scalable, which means if it is working for 10,000 samples today and giving you 99% accuracy, that's good, but it's not good enough. It has to be scalable. If the scale you're looking at is millions of data points or billions of data points, it has to be scalable. So the engineering solution that has to go in is equally important. Second aspect is generalizability. Even if you got let's say 1 million samples today and your solution is working at that scale, if the framework was trained on, let's say, a few 100,000 samples, then you have to have a way through which you can convince at least yourself that the solution is generalizable, which means you have some held out data on which you've evaluated the system and you were able to convince yourself that the accuracy that you saw on the data that was used for training remains pretty much the same on when you compute the accuracy on the held out or the data that was not seen. Oftentimes I have seen in my experience that the generalizability component is not given as much importance as it should be, and this becomes very relevant especially in the big data dynamic nature of data kind of a situation. Okay, so let's dive deeper into this component of number 4, which is how do you pick the framework. What you see here is a representative graph where I want to make a couple of points. On the x-axis, you see the time taken or any other consumption of resource. And on the y-axis, what you see is accuracy or any other metric that you would use to evaluate or quantify your performance. Now, typically what happens is the law of diminishing returns will kick in after a while. What that means is in the beginning, as you're spending your resources, the jump in accuracy or whatever else metric you are using will be significant. But then after a while, you will hit the asymptote, which means the amount of effort that you would put in to get even a small improvement in your accuracy will be huge. And so you really have to get the executive support or get your people to rally behind your project so that that huge amount of effort gives you that tiny bit of increase in the accuracy. And that's where your foundation or foundational work that goes in becomes significantly important. And so now I'll read out the statement that I've written here, which says the foundational work has irreversible impact on when and where. When is at what time point, where is on the y-axis, at what accuracy point does your solution reach point of diminishing returns. And so if you took one foundational, one approach of the foundational solution, this is the graph you would look at. A better thing would be to do this. And this is where now what you see are two things. The when part has moved quickly, so within a short period of time you reached the asymptote, and where part has moved up in the y-axis, which means the accuracies at which you have point of diminishing returns have also gone up. And so this place is often where a lot of the efforts are overlooked. And I would encourage everybody here to, as they're looking at problems to solve, to take a step back, figure out what is the foundational approach that they have taken and where would they reach the asymptote. And again, I don't have a specific prescriptive solution at this point for what the foundational approach should be, mainly because the approach depends on the problem you are solving. But what I will do in the next few slides is give you ideas on some of the broad things that you should be looking at. Specifically, what is the subjectivity that that machine learning has, and how do you account for it? And second is, what is the objectivity that the machine learning has, and how can you utilize that objectivity so that it really solves the problem that you have in mind. So those are the two things I'll cover: subjectivity, objectivity. The third piece is, how can you bring in the advances that are happening in the machine learning field to really address the dynamic nature of your data. So that's the third aspect I'll cover. And then I'll go into some of the other steps which I had narrated. Okay, so let's move on. The first one is the objectivity part of it. What you see here are three pictures. And let's say this is not an image recognition problem, but this is a real life problem where you are navigating through a wildlife sanctuary or through a jungle. And the problem is, you may encounter a cat or a dog or a leopard. Now, if this was an image recognition problem, a toy problem of image recognition, you would be forgiven to say that the error of recognizing a cat as a dog is exactly the same as the error of recognizing a cat as a leopard, right? So you give the cost of 1 for both of these, and that's what I've drawn here. But now in the real world, the situation is very different. The error of recognizing a cat as a dog is a lot less as compared to recognizing the cat as a leopard, right? In the jungle navigation situation that I talked about, hopefully you can relate to it, that you may not be, as affected if you recognized a cat as a dog in that jungle, but if you recognize that cat as a leopard, or the other way, you recognize the leopard as a cat, then you are in a lot more trouble, right? So that's where your definition of what is a error becomes very important, and that's where the cost function that you're using to train your machine becomes very important. Once you fix the cost function, your machine is now with a very singular focus going to optimize all of the parameters so that that cost function is minimized, right? So it's very important that the cost function that you have in mind is in line with the business problem that you're trying to solve. So what I'm showing you on the right hand side are three different cost functions, very simplistically again. The first one is a linear, which says, okay, by the way, on the x-axis you have the ground truth, and on the y-axis you have, or rather on the x-axis what you have is the deviation from the ground truth in your prediction, and on the y-axis you have the cost that you're going to pay. The linear function basically says the more you are away from your ground truth, the more I'm going to penalize you, or the more time I'm going to spend executing, trying to figure out the right the right answer and so on. So that's one cost function. The second cost function is typically used when we are okay with rounding off errors. If the answer if you say, give me an answer which is the closest integer, then you are okay if the actual answer was 10, but I guessed between 9.51 and 10.49, right? So that is where you have stepwise linear kind of a function. And then there are some cases where you are okay if the animal that you've recognized is wrong, but as long as the confusion is within the domestic family of animals, and you're not confusing a domestic animal with a wild animal. So if you have that kind of a situation, then the rightmost graph is what you would use as your cost function. Okay, so that was the objectivity piece. Once the objective function is fixed, there is very little you can do in terms of adding more data to improve the accuracy, unless you go back and change the objective function itself. And I've seen people make those kind of mistakes too, where they pick the wrong objective function compared to what their real business goal was. So that's one aspect. The second aspect is that of subjectivity. Typically, our machines today are trained using the supervised learning paradigm. What I mean by that is there is a supervisor, which in this case is the human expert, who provides labels that the machine will then use to learn. So a very simple case I'm showing on this slide is that of distinguishing red color from green color. Everybody who's looking at this will be able to very clearly distinguish which is the red one and which is the green one. So the data that you would get from the human experts in this case, it has less subjectivity, and so the machines that you would train are going to be highly accurate, right? But remember that the machine that you're training will only be as accurate as your data is consistent. And so that's why there is a whole field of research called R&R, or not roles and responsibilities, but repeatability and reproducibility. So what does repeatability mean? It means the same task is given to the same human, and the human is now asked to repeat the task. And then you check how many times did that same human agree with his or her own judgment across the different trials. The higher it is, the simpler or less subjective the task is, and that's called repeatability. Reproducibility is when n different humans equally skilled in the task are given the same task in the same environment, so that they're not affected by any ambient noise, and you check how many times do these humans agree among each other. That's the reproducibility. Now, as you can imagine, repeatability will typically be higher than reproducibility. And as the task gets more and more complex, the repeatability and reproducibility goes down, and that's where subjectivity creeps in. So in this example of distinguishing red versus green, I can make this a little complex or a little more subjective by saying, instead of just those two colors, I have this palette of colors. Now what happens is there may be some who may look at this particular, one particular color here, which is the horizontal on the left side, and say, that looks like navy blue. Others may say, no, that's dark blue. Yet other group may say it's violet, right? Similarly, some may look at the color on the right side towards 1 o'clock or 2 o'clock, and some may argue that it is dark yellow, the others may argue it is orange. This subjectivity will then directly lead to inefficiencies in your machine's output. And so what has to be done is, as you're generating data, you also have to account for this subjectivity, but then do a rigorous exercise of what we call human calibration, where all the humans who are going to give you data are um, calibrated to look at a particular data sample and give one particular data label to it. Okay, so that is where a lot of subjectivity comes in. Now, remember in the first step that I said was how do you define the what is the machine learning problem that you define? A lot of how you capture the data and the amount of subjectivity that comes into your data depends on how you have defined your problem also. For example, in this, if I define the problem as what is the color on the left bottom, that's a different problem versus identify where is the pink color. Depending on how you pose this problem, the user feedback will be different, and hence the amount of subjectivity that you will have will be different. Remember that the problem that you have posed to the humans has to be near exact to the problem that you're going to pose to the machine so that you reduce the subjectivity. Okay, so let me take a quick pause here. And Ankita, do we have a couple of minutes to take questions?
Yeah, we have few questions. So let me just start with the first one by Rahul. He's asking that which all technologies are required to be known by a product manager and in how much depth?
Okay, good. That's a very relevant question. Um, so so the reason I'm pausing is there is no real correct answer, no one correct answer for this. I'll tell you from my experience how we interact with our product teams and how we work with the product managers here. The one thing that the product managers, the one value that the product managers bring to the table is understanding what is the end use case that the end user, be it a corporate client if it's a B2B company, or the end user if it's a B2C company, that uh, that the end client is facing. And then jointly with the engineering heads or the data science heads, you would have to figure out what are the ways in which you would solve it. Okay, now to your direct question about what are the tools that the product teams have to know, I would say uh, instead of exact tools, some of the domains that the product teams would have to know are: A, what are the sampling techniques that you would use to evaluate your system? B, how would you quantify your numbers? So what are the techniques through which you would quantify your accuracy, which sort of ties with your sampling technique? And C, which is very important, is what is the UI UX that you would have? So what are the kind of usability tests that you would do to see what is the impact that inaccuracies in your machine learning system, how are those inaccuracies propagating towards the end user?
All
Okay.
right. So the next question is by Rituraj. He's asking that how to formulate all the data in AI ML framework. Is there any formula or train it manually?
Yeah. So um, unfortunately, the answer is no. There is no formula, and that's where it's still a art form. That's where you still have to do what I called early on as data swimming, understanding your data, understanding the depths of the machine learning framework that you're going to use. There are, however, a few things that you can do, and I alluded to some of it earlier. One is, imagine the ideal scenario where a human expert has all the resources at his or her disposal and also has all of the labels that are needed. In that case, what are the the dimensions of the data that a human has used to make a decision, right? And then try and see how you can now replicate those dimensions in your data. As as you do this iteratively, you will figure out what are the gaps in your data, and also what are the biases that are coming in from your data.
All right.
Okay.
The other question by Saddam is probably he must have written while you were, on one of these slides. The question is it related to testing of hypothesis? So if you are able to decipher what he's referring to, Om.
Right. So earlier I talked about, um, he might have typed this right in the beginning when I said the experts have to come up with hypotheses and test them.
Yeah.
That is true, but there are also, in the statistical world, there is a field by itself called hypothesis testing. These two are slightly different.
Okay. So,
Okay, can we take one more question and then go back to the session?
sure. Sure. So the last one is the framework would support interims of data privacy, in brackets scalability.
Data privacy and scalability, these are two different things. So by putting it in bracket, I don't know how would you relate to the two, but let me try and address both of these. The framework, if you know beforehand that your data has to be securely guarded, then you have to incorporate for that dimension as you're coming up with your framework. Now, if the question is, I want to have a scalable system while at the same time retaining the privacy, then there are a whole different class of frameworks where you can have what are now called privacy preserving ML formulations, which with the advances in the technology are also quite scalable.
Okay, I guess it answers his question. So let's just resume again, Om.
Sure. Okay. And so so just a quick time check, Ankita, then what I will do is stop around 3:15,
Uh,
3:20. Is that, and then we can
oh,
take.
yeah, 3:20. It's perfectly fine, or middle of 3:15, 20 Om anytime. So then we can have
Perfect.
a few other
We'll do
questions.
that. We'll do that. Okay. So now, so far I talked about two main components, the subjectivity and the objectivity. Now let me bring in one example of a domain expert, and this is a bit of a uh, uh, concocted example, but hopefully you will see what I'm talking about. Let's see, you see some data on the x-axis, on some on the y-axis, and without knowing what the x-axis is and what the y-axis is, which is where the domain expert would come in, uh, the machine learning expert is now asked to fit a curve. What would the person do? He would say a linear model would fit in, because he or she doesn't know what the x and y axis represent. But now if somebody told you that this is coming from the domain of magnetic field or magnetic studies, then immediately the domain expert would say, as you increase the intensity, there's going to be a saturation effect, and so the linear model is not going to work as well. So then immediately you're going to change your model to say, okay, in the beginning I'm going to have a linear model, but later on I'm going to sort of maybe continue with the same with the linear model, but change the slope and hence make a piecewise linear model. Or there are cases where you may have to model hysteresis, and then again you will have to come up with a different model. The point I'm trying to make here is, in today's big data world, where as the amount of data you observe increases, your understanding of the system itself will change, and hence the model that you are using may also have to change. But instead of changing your model fundamentally every time you see different sections of data, what you ought to be doing is providing flexibility in your model so that it itself can uh, can learn different parameters as the complexity of the data is changing. And folks who are familiar with the research domain of BNP or Bayesian non-parametrics would appreciate that that is the area I'm alluding to. So I'll give you a very simple example here. I show you these samples and I say guess the number of clusters. Pretty obvious, you will guess 2. But now let's say I add more samples, you would still say, k remains 2. But now as I add a lot more samples, suddenly k is equal to 2 is no more the only possible answer. Now you're entering the gray area that maybe there are 3 clusters, maybe there are 4 very closely associated clusters, and so on, right? But if you started off with k equal to 2, then even if you change your uh, objective function or the distance metric in this case, you fundamentally made a decision of k equal to 2 and you will never reach the optimal solution. And that's where I want to give you an analogy of how we as humans don't have a set number of clusters in our mind, and we learn the number or we change the number as we as we look at more and more data. So here what I'm showing you is how we as humans learn that the uh, number of different kinds of vehicles that are possible uh, can change over as we are exposed to different vehicles. So as a kid growing up, you would just look at this and say, okay, this is the one and only vehicle that you would have. Maybe at some point you get a bike ride, and then suddenly nobody has to tell you that this is the same thing as what you were riding when you were a kid. You suddenly, your brain has learned that initially when k was 1 number of clusters, now I have k equal to 2, and these two are 2 different clusters of the same family, which is vehicles. Further down, you may look at this kind of a vehicle, and nobody has to explicitly now train you. You automatically know that this is the same thing. It has tires, it hits the road, you can commute from one place to the other, and so on. Eventually, if somebody shows you this kind of a picture, you would still have no difficulty in in predicting or in appreciating that this is also a vehicle, right? So humans are pretty good at increasing the flexibility of their modeling as more and more data comes in, and that is really where the area of BNP, this is an area where I have spent a lot of my time researching. We at Yodlee are also using this quite a lot, especially the first and the second topic here, Gaussian process and Chinese restaurant process. GPs help you change the correlation function as your data changes. CRPs, or Chinese restaurant process, help you change the number of clusters that your data may fit in as the amount of data changes. And so if people are, people in the audience, if they are looking at data which is highly dynamic in nature, and if they're struggling with changing their model topology constantly, I would encourage them to look at these two topics. IBP is also a BNP framework that is used when the underlying dimensions which represent the data would change over time, or would change as the amount of data changes. Okay, so I wanted to just give you a glimpse of some of the deep research that is happening in the machine learning framework, and how you can use some of it in your real life situations. Okay, I know I rushed through this, but folks who are interested, please, I would encourage you to Google for these topics in the red side, written in red, and if there are any questions, we can discuss those offline also. Okay, so now very quickly, let's move to the seventh step in this, which was how do you get the system to be generalizable, and how do you get the system to be deployment efficient. So typically what happens is, so what you see here is the power law. X-axis is the data instance, y-axis is the number of occurrences. Typically have the 80-20 rule. 80% of your data falls within 20% of nuances, and the rest is what we call as the long tail. Handcrafted rules are good enough for the top head, or what you see in the green here. And so a lot of the times we fall into the trap of having a system that works really well for these top head data instances. We declare victory, but when it goes in the hands of an end user, the end user more often than not would be in the long tail, or elements of the end user would be in the long tail, and that is where Rahul had a question on what the product team should be doing, or how do you take this to the towards the end product. You would really test the system for its generalizability, which is the problem of exploring the long tail. Everybody has this problem. Netflix paid $1 million to solve this. YouTube has this. All of the e-commerce companies have this. How do we get that obscure customer to buy some of the obscure products which have high profit margins and so on. All of that is the area of exploring the long tail. So you have to absolutely look for how generalizable your solution is, not fall in the trap of the top head, where the system, even a reasonably good system, would give you highly accurate numbers. Okay, the next problem is how do you make the solution be efficient? And I want to say what Netflix had to do. In the interest of time, you should just Google for what happened to Netflix $1 million solution that they the first prize that won the $1 million solution. They were not able to put it in production because of engineering costs. Okay, so there are ways in which you can do this. In the interest of time, I'm going to skip through, because what I want to do is come to the UI UX part. The idea here is, when your system is highly confident, you want the UI UX to reflect it. And where your system is not confident, you want to have a way in which you let the user know that the system is not confident. Please either provide inputs or just work with that that uncertainty. So here I've searched for Prime Minister of India, and Google in this case is very confident of the answer. So it didn't even give me a link right away. It just gave me the answer, and turns out the answer is correct, right? And of course the first link is also correct, but the answer itself is correct. Google was confident, so it gave me the answer. On the other hand, when I asked a slightly different question, where do the MPs of India meet? Google got the answer correct, Parliament of India. Second link is also correct, Rajya Sabha, but wasn't very confident, so it didn't give the answer as the first flash. It gave me the options, right? And that's the beauty of sort of camouflaging where you may have ML shortcomings. A much more relevant example is that of spell checks, or spell checks that you would use in any of your document writing tools. If you type TEH, this is the most common mistake. Spell check knows that there is no such word as TEH, and so it would automatically correct it to the. On the other hand, if you type something like this, visit palace, the spell check knows that there is error. It's not 100% confident, and so it gives you an option of what the likely correct answer is. Now contrast that with the third case, where you've typed some garbage. It has highlighted it as mistake, but it is not even confident about any of the possible words it has in the dictionary, so it's not giving you any answer. It's just saying no spelling suggestions, right? Okay, I'm going to take 30 seconds to say what is it that we are doing at Yodlee. We are putting all of these things to use in Yodlee to identify what are the sort of financial transactions that go through our system. For example, whether you went to a Walmart or whether you went to a H&R Block, which happened to be housed in a Walmart, and so on. So those are the kind of problems that we are solving. A lot of work around deep learning, deep machine learning, NLP, to solve real world financial problems. Okay, with that, I wanted to hand over to Ankita so that she can talk about what is coming next.
All right, thank you, Om. So let's just start with a few other questions. So the first one here is by Khalil, who's asking two questions in one go. He's saying, I want to start AI/ML practice in my organization. Which tool I should choose first? And the B part of the question is, or I have to start with Python algorithms for supervised and unsupervised.
Okay, so this is a very broad question. If you are starting off with so if you're starting from scratch within your organization, again, the answer will depend on how big your organization is, how much of a risk appetite you have, how much data you have, and so on. But generally speaking, uh, I'm going to assume that you're starting from scratch, and the other dimensions are reasonable. Uh, what I would recommend is just first formulate what is the problem that you want to solve. And then go down the path of whether you want to do a supervised learning, whether you want to learn Python, or whether you want to just use something that is off the shelf, and so on. So if you're starting from scratch, my recommendation is first focus on what is the problem you're trying to solve, and then look at the paradigms that are most relevant.
All right, I guess it answers his question. The other one is by Raghuveer. He's asking that, has any real-time solution slash POC done in India? If yes, can you give a brief overview?
Um, so I can talk about what we are doing. We are based out of Bangalore, and so we have a lot of financial transactions of users, and our idea is to help the users be able to interpret their own financial transactions in a easy and quick way. So let's say you shopped at More, or you went to a mall and you bought a PVR ticket, and then you also bought something else at one of the one of the stores there. Typically what would happen is, and let's say you used your credit card, so basically you paid through a channel that led to a digital trail. The message that you would get either on SMS or on the web page has a lot of gibberish to it. Our goal is to uh, process it quickly, near real time, so that um, the message that gets displayed when you log into the system later on is not that gibberish, but what we call a simple description, which says, this is the merchant you went to, this is the amount you spent, and so on. So that's one example. There's a lot of cool work that is also happening in India around e-commerce. A lot of cool work happening in education analytics, where some of my colleagues are looking at, ex-colleagues rather, are looking at analyzing educational videos. Some other folks are looking at analyzing healthcare data, or analyzing healthcare images, and so on. So there's actually a lot of very exciting work happening in India around data analytics, be it for text, which my company is doing, be it around images, videos, speech, just a lot of work happening. Yeah, very exciting times actually now.
Yeah, I completely agree with you. The next question is, how can we adapt our system from one model to another with change in the environment?
Right. So uh, on one extreme, this continues to be a deep area for machine learning research, uh, where areas like domain adaptation, transfer learning are coming up. On the other hand, so people who are interested on the deep machine learning side of this should look for things like transfer learning, domain adaptation, um, covariate learning, and so on. On the other hand, a lot of the times, if you are in a hurry, or if there are intense pressures from a product delivery perspective, it's good to have your model to be decoupled from uh, from the from the nuances of the data that you're using. And I can't think of an appropriate example in the next that I can finish end to end in the next 30 seconds. But don't have your models very tightly coupled with your data, so that when your data changes, you can still reuse your data. Uh, some of the deep learning architectures are pretty good at doing that, where some of the initial layers you can train on generic data, and then the top layers you can bring in your own data and reuse.
Okay. The other question is exploratory data analysis performed better through Python or using visualization tools?
Depends on how how much of a depth you want to get into. But assuming you are into coding, or you have the person who's asking the question has a team, or he or she himself or herself is into coding, Python by far has a lot of tools and libraries which will let you look at the data in a variety of different ways. Pandas is one good tool that you can use to just slice and dice data. Of course, there are visualization tools also. So if you're not so much into coding, then visualization tools would be better. But if you want to code, my vote is always for Python. I extensively use that. My entire team uses that.
Okay. Shraddha is asking you that are there any books you would suggest for a beginner of AI and ML?
Okay, yes, I would suggest books. Not one book, but a variety of books. So Tom Mitchell's book, that helped me learn quite a lot. That's a good book. Uh, but today, actually, there are quite a few videos on YouTube which can help you get started. Some that come to mind are, and again, I'm not advertising on behalf of anybody here, but you can probably just look at the channel that Mathematical Monk has on YouTube, the Coursera course that Andrew Ng has on YouTube, uh, his Stanford course, which is also on YouTube, is also very good. Tom Mitchell's book I mentioned is good. If you're into deep learning, there are quite a few books, and quite a few videos also online that can help you.
All right. The next question is, how do we decide the extent we have to camouflage our data in the UI UX, like how big the data set needs to be without compromising the response time?
Um, it depends, and I'm sorry if all my answers are it depends, because it just shows the complexity of the machine learning world, and also to some extent it shows that there is flexibility based on the nitty-gritties. You can always find an answer that is most appropriate for the user. But let's say you the compute cost and the compute environment is not a challenge, which means you can use one of the cloud environments. Then you can scale, you can reduce your time to meet your real-time requirements by scaling on the cloud.
Okay. So I guess this will be the last question looking at the time. So it'll be how do we know the latest trends in AI in our specific domain? I mean, like in the respective specific domains, I guess so.
Say that again, sorry.
How do we know the latest trends in AI in our specific domains? Quite an
Okay.
open-ended one.
Yeah. So it's yes. I mean, it's good. Most of the questions are open-ended, because then I can, give you the entire range of possible answers.
Yeah.
So if you are if the you know if you are a machine learning researcher, one extreme, you should look at Archive, ARXIV, which has papers coming out. It's a very vibrant community. Or you can look at other peer-reviewed conferences which also publish their papers online. That's one extreme. The other extreme is Quora. Gives you good good ways to stay in touch. I would actually encourage NASSCOM to also have some forums where people can come together and discuss this. What is happening is this field is just changing so dynamically that you need to just, and the information is coming at us from so many different directions. You need to really be plugged into a variety of different social channels. I follow a bunch of people on Twitter. I don't do Facebook, but I follow a bunch of people on Twitter. I follow a bunch of people on Quora. I I'm on. I look at archive every so often, um, and then within our organization we have people presenting papers or topics every week, every other week, every month across three different types of forums. So you can do that. Within your organization you can have people on one extreme talk about a deep technical problem, on the other extreme talk about a pure business problem, and then that'll get ideas going. That'll help you also generate ideas as well as learn what is happening in the field.
All right. Thank you so much. Now, as you know, we are just running out of time. So thank you, Om, for this insightful session. And I'm sure everyone learned something new, and it must have answered their questions which they must have faced in the past. The traffic we saw on the platform indicates it was a houseful session. So thank you, Om. Plus, I just want to tell my audience that NASSCOM Product Conclave, our flagship event, is coming up in October on 25th and 26th of October in Bangalore. So you can always log in, register. You can log in through our website www.nasscom.in and register yourself. And there are so many interesting things, summits, interactions coming up. So we would love to see you over there. And thank you so much, Om. And looking forward for other associations with you for the forums you have just advised and everything. So thank you so much.
Yep. Thank you, everybody, and thank you, NASSCOM, for this opportunity.
Thank you. Thank you. Okay. All right. Bye. Bye for now. Take care.
Yeah.